Hello, everyone. It's a pleasure to welcome you to this session. So to start off, I will introduce Dr. Jim Nelson, although I suppose many of you know him. Dr. Nelson is a professor of civil and construction engineering at Brigham Young University in Provo, Utah. He has been a pioneer in developing geospatial hydrologic modeling and hydroinformatic tools, and is the principal developer of the Watershed modeling system, which since the 1990s has been widely disseminated and used for development of hydrologic models and visualization of results. In recent years, he and his colleagues at BYU developed Tethys platform, which is a free and open source tool that lowers the barrier for engineers to create web applications for hydroinformatics. Tethys has been foundational element of the GeoGlows ECMWF Global Streamflow Services, which provide an 80-year historical simulation and 15-day forecast on every river of the world daily. Dr. Nelson, the floor is yours.
Thank you. It's an honor and a pleasure to be here today with you in this beautiful country, and the opportunity that we have to talk about space technologies and their ability to inform us in making critical decisions. And I want to speak just a little bit today about the GeoGlows Global Group on Earth Observations Global Water Sustainability initiative that we've been developing global water information, hydrological information. First of all, just a little bit more. I come from Brigham Young University. This is in the state of Utah in the Western United States. And it's more, you probably more commonly know us for the missionaries that go out throughout the world. And this activity allows us to learn cultures, languages, and these students come back to BYU with a strong desire to contribute. Let's see if it will advance. There we go. So there's twin mottos at our campus. The world is our campus, and enter to learn, go forth to serve. And so motivated by these experiences that they have worldwide, they have a desire to contribute to the improvement of conditions worldwide in many different ways. I work in the hydroinformatics lab, so we're interested in developing information and sharing that, making it available for decision-making in water resources. I always like to share a picture of my most important co-collaborator, my wife, Laurie. She's actually here with me, not this morning, but I wouldn't be able to do the work that I do if it weren't for the support that I get from my family. This is my family, 4 children and 9 grandchildren. And so wherever I go, I always try to remember these are the people most important. And I hope if you remember nothing more from my presentation today, I hope you remember to go home and thank your most important co-collaborator and the friends and family relationships that you have that make this possible. All right, so what is GeoGlows? GeoGlows is, again, the Group on Earth Observations Global Water Sustainability Initiative. It leverages partnerships around the world to develop open and accessible hydrological information on a global scale. It's really a story about a great collaboration. You notice the picture at the bottom is a rowing team. Recently, there's a movie out called The Boys in the Boat. This was a remarkable victory of a rowing team from the University of Washington that went on to win the Olympic gold medal in 1936. They did it against all odds by amazing teamwork. And that's what the GeoGlows project has been, a team that comprises not just our hydroinformatics lab at BYU, but NASA and their SEVERE program and the GEO program that has provided funding, also NOAA. Of course, ECMWF, where the forecasts come from, the World Bank, Esri, Aquavale are the principal, but there's many others that have been involved. Mandira here from ECMOD. This was our first project was in the HKH Himalaya, and so much of this work emanated from a collaboration that we did with them. And so what I'm presenting today really is a remarkable accomplishment, but only made possible by an amazing collaboration and teamwork together. So when we speak of global security, global water security, what do we mean by that? I mean, there's a lot of definitions, but I like this one, water quantity and quality for livelihoods, ecosystems, and production. And plus, we have to remember that that's connected to acceptable water-related risks to people, environments, and economies. And so that's what we're striving for. And of course, it reflects well in the Sustainable Development Goals. And you can see I put a check mark here on many of the Sustainable Development Goals depend on water and having adequate information for making decisions. And I focus primarily on floods and droughts, water quantity, but many aspects and that water quantity is important for all the other aspects that we deal with. So if we're going to attain water security, we need to have actionable information, not just data, but we have to have it compiled in a way that can be used to make actions and make decisions. Without actionable information, it's impossible to have global water security. It's impossible to have water security at any location. So when it comes to hydrology, the gold standard has always been observational data. Can we measure data? And interestingly, when we have a crisis, a drought or a flood, everybody wants to know, well, why haven't we been gathering information? But when the absence of these crises, then there's little investment in this information. And so we really are at a lack of information from observations. And this is where space observations and technologies and global models can play a pivotal role in providing and filling those gaps to give us the information that we need. So that helps us improve water intelligence, and it's our responsibility as scientists, in my world as hydrologists, in order to develop that information so that we can make more informed decisions about the management of our water resources. So GeoGlows then provides, and you can think about it, what if you had 80 years of hydrologic record on 7 million rivers worldwide? What could you do with that? How would that inform your decision making? And this is what GeoGlows is producing now, and it's open, accessible, hydrologic record on rivers across the world at a scale of about 25 to 30 square kilometers, watershed size. Then what if you can add a daily forecast on each of those 7 million rivers? And so we're working with ECMWF. We then take their meteorological forecast, their 15-day forecast, and provide that as a hydrological outlook, river discharge on each of the 7 million rivers worldwide. And so that's put together as a service. So running since November of 2020 operationally on the supercomputers at the European Center for Medium Range Weather Forecasts is this downscaling of their meteorological forecast onto a river network, a routing of that water through those networks, and then a data service. There's a historical data service, a forecast data service, and a mapping data service. And those can be combined. They're open, accessible. They can be combined in applications so that they're made individually at a given river or collectively across a watershed, a region, a country, to provide that necessary information for making hydrological decisions. Now, there's a lot of benefits of a global model and the use of satellite data. And I would suggest to you that a lot of the technologies we're talking about, while resolution in both temporal and spatial might not yet be adequate for all the applications we want, they're only going to improve. And I use the example of Google Earth. I remember 25, 30 years ago when these images first started coming out, they looked a lot like this, but it was amazing. It was a miracle that I could zoom around the world and I could get satellite imagery of any location. Many look like this with very low resolution and clouds, but over time, that improved. And everybody who was using the system benefited by those improvements. Okay, today we get very high resolution. In fact, Google Earth now does 3D Street View. And so it's populated with pictures and information that is a treasure. And this is the same thing that's happening with the Global Water Sustainability Program. The resolution's only improving, the information is improving, and as people begin to use this information, they're only going to benefit by those improvements to everyone. So here's a couple of examples. This is if we have global water intelligence, these are the things that we can do. And this is an example in Malawi in 2022. They had a community-based early warning system. So they had gauges installed upstream, and then they informed when they began to get an extreme event, the communities downstream. But this only provided for a couple of hours of lead time. And because of that, often people, property couldn't be moved in time. And so they suffered property damage and loss of human life because of that. By implementing the GeoGlow service on those rivers, they were able to now have a days in advance warning. And so they actually now could be prepared. Then when they saw the signal, everybody was already in motion and they could move. And so in 2022, they had a couple of cyclones that came through this area. And afterwards, the president declared the success had been that not one person had died during that rainy season. And they estimated a savings of over $40 million because of the community-based system and the early action that they were able to take. Another use of GeoGlows and the kinds of things that can be done was in Ecuador. Here there was an indigenous community, largely of women, because many of the men had immigrated into town for work and other opportunities. They had the need to design an irrigation system, but they didn't have the information available that would tell them what's the quantity, what sizing for the infrastructure they would need to be able to do it. And so using the historical information from GeoGlows, they were able to come up with a design and then be able to get approval for and construct the irrigation system that now supplies water to a community, and livelihood and economics in that area is increased. Here's another example where we have the information, but it's not actionable. We were not able to use it. This happened in Libya last September. You may remember the floods that happened in Derna. And in this case, there were heavy rainfall forecasted. 30 million cubic meters of water already came down into a flooded area. Much of the city was destroyed. Now, I don't think that could have been prevented, but the warning would have allowed people to move and save the massive loss of life that occurred during that event. It happened largely because there were dams upstream, and they became overwhelmed by the water, and they burst. And that, again, that was probably not preventable, but the warning should have been there. This was the location, the river in GeoGlows along that area. And it's difficult to see, but there's the event was largest event ever, and only one was only about 15 cubic meters per second that was recorded. And so in this case, even days in advance, there was a high probability of a forecast upwards of 4 to 5 times the largest event that they had seen in that area. And that, of course, information was there, just not ability to communicate that and use it in providing their warning. So at BYU and through our partnership, we're now working with different agencies around the world in order to be able to provide this warning, not just to have the information, but in the Early Warning for All program, to be able to communicate that, to be able to respond and use that as part of that information. And so with that, I will conclude my my address, and just with a reminder that these technologies, this kind of global information is empowering us. We need to be able to find ways in order to communicate that information, get it into our decision-making process so that we can benefit all of those around us. With that, I don't know if I have time for questions or if you want to. Okay. And if there's no questions, yes, go ahead.
Say your name.
Morning, Freddy Soria, Universidad Católica Boliviana. Professor, very interesting presentation. How do you get the data from countries, from remote areas, for example, from the national agency, or you collect the data from other sources?
Yeah, so actually, we don't collect as much data as we would like to, but we work a lot with the World Meteorological Organization. We're trying to encourage them to share their data. What's not presented here, but part of the workshop that I will give tomorrow is how we use local information to improve the global model by bias correction, which does it not only in the regions where we're able to get data, but then it improves the whole network, especially in that region and local region. So we are working to encourage those agencies to share whatever limited observation data they have in order to improve the entire network.
Good morning, I'm Miriam Villalobos. I am from El Salvador, and I have a question about the GeoGlobes, because this model is global, right? In El Salvador, it's a small country, and I saw the platform, and we have just one river or two rivers in these applications. Is there any way to do a model like this, but in the regional scale, like Central America, for example, to do more details to the other rivers?
Yes, and so with the latest version of GeoGlows, it actually covers many of the smaller rivers in El Salvador and Central America. I was in Marne last fall, actually, and I'm working with them and their meteorological forecast also to provide more localized flash flood forecasting. And in our work in Nepal, when we were at ECMOD, they also have a high intensity weather forecast that we were able to adapt to the same river network. And so, yes, these are opportunities. The global model itself is a medium range weather forecast, but we're working with countries throughout the area in order to adapt their own forecasts and modeling systems into it.
Thank you very much. This was really useful for us.
Thank you. Okay, I think we'll go ahead and continue.
So just to provide some information that's already in the program. So for this first part of the session, we'll have 5 more presentations, and we'll break at 10:35 until 11. And then we'll continue with the second part with 2 more presentations, and then we will have a 30-minute Q&A and discussion section. Okay. So next up, we have, oh, by the way, each presentation has 12 minutes, and then we have a 3-minute, very short question period. And then, but if that's not enough, we still have the 30-minute Q&A and discussion section at the very end of the session. Okay. So next up is Amjad Ali with the presentation titled Quantitative Assessment of Land Degradation in Watershed Using Space Technologies. Thank
you. Okay, very good morning. Today I'm going to share with you some results of a study or a project which we are going to implement at a country level, which we call NatCat project, that is a natural catastrophe model. But out of that, I'm going to present only a small study related to the erosion modeling, and then followed by, how we can come up with identifying the potential dam sites. So this is the storyline which I'm going to follow, more or less. I will reflect on the context, and then it followed up by the methodology, and I will share the results of the 2 case studies, and then we can end up with the conclusion. For any business related to food and land to be sustainable and profitable, it should have been economically viable, it should have been socially acceptable and environmentally safe. And if you want to make any activity sustainable, then you come up or you face some challenges. And these are some of the challenges which I have mentioned here. And these are common in every part of the world. Like the agricultural activity and the food supply is no more sustainable because we are now investing a lot, but we are getting very less out of that. So to make it sustainable, one has to struggle a lot for meeting the both ends. Similarly, another important impediment in this whole context is the access to innovation. Even if there is any innovation in any capacity, that is not available for the community at large. So unless you dictate the whole system with innovations, they are not going to make any difference. Similarly, low productivity, as I have already mentioned, that most of the agriculture forms are now operating at a very low productivity level. So that low productivity is also exacerbating the problem at large. Adaptation to climate change is another important thing. A lot of people have talked about it more in terms of the hazard associated with it. But I think if you're not well adapted to the climate and its changes, then you are also not going to make a profitable business out of any activity related to food and land. Now come to the actionable information. Again, everybody is not having the access to spatiotemporal information. We are very few people. The remote sensing community is only having the capacity to give the actionable information that is explicit both in space and time. Until and unless you're not having a spatiotemporal explicit information, you're not going to make an informed decision making. If there is no informed decision making, opinions are not going to make any big difference. Similarly, the water efficiency, very roughly, I can say that 70% of the agriculture activity is still dependent on flood irrigation. Very few people are now resorting to the modern techniques of giving the, area specific or requirement specific irrigation to their crops. Climate change impacts in terms of the hazards. Again, a lot of people has talked about it, droughts, floods, sea level rise. They are also affecting this particular activity. Environmental concerns are also important, and you cannot really ignore it. And it is important in terms of the land degradation from the unsustainable practices. Similarly, the waste disposal and the pollution eutrophication are also important phenomena to consider. Okay, just to put the discussion in context, we have to just reflect a little bit more on the interplay of the terrain, rainfall, and land use. And if you are not, taking care of all these aspects, then there are some on-site damages due to this interplay, and there are some off-site damages. Some of them are only mentioned here. This is not an exhaustive list. Soil quality deterioration is one of the most important aspect that is affecting the sustainable land use and land cover and agriculture practices. Similarly, soil fertility losses, both in terms of the soil physical and chemical properties and the organic matter present in the soil. We are having a decreased crop productivity and also the land degradation. Land degradation can be taken in a different perspective other than the soil fertility. Similarly, diminution of the landscape beauty and destruction of installations. Similarly, in off-site damages, if we consider, there are some of them which are important to mention here, that is siltation of water courses and reservoirs. This is one of the most important thing that is affecting mostly the irrigation network that is available throughout the world. Similarly, the water quality is also deteriorating with time. The eutrophication is affecting a lot the ecosystem that is dependent on the water that is available from upstream up to the deltas. The disruption of the water ecosystem, the effect of the toxic organic and inorganic material like the pesticide, and also the fertilizer, the heavy, doses that we are applying actually to increase the productivity of the crops in many regions of the world. Similarly, the turbidity disturbance, the ecosystem and the dead plants, and the disturbed condition for fish and other aquatic organisms. These are some of the things that is going to affect a lot the land productivity perspective of the agriculture and or any business related to the land and water. So let me share the example related to the erosion modeling. Space technology is very helpful because you have a lot of information for a large area, and you can also cover the spatio-temporal context. You can not only study when, where, what, how, so you can even relate it to the causes and effects. So that particular aspect is very important. Let me give you the example of the erosion that we have done for only small segment of, the Pakistan. You know that Indus River is Pakistan ranked third in the world with an annual sediment load of 435 million tons. About 13 million hectares, the area is affected by water erosion. And Indus River is alone bringing around 500,000 tons of sediment to the Tarpela Reservoir. Tarpela Reservoir is a dam which is available upstream, not even downstream. Even then, it is bringing so much, sediment load into that particular reservoir. Sedimentation of canal irrigation system is decreasing water and water use efficiency. And this is all just because of the lack of the information on temporal and spatial scale. And similarly, the non-availability of the erosion risk. So here I'm going to share with you the study of Potohar region, which is situated atop of the world's largest irrigation network of canals, the Indus River system. I have used the very well-known and well applied in all parts of the world. That is the Russell model. So that Russell model is really very simple to use, and it encompasses almost all the elements that is necessary for erosion risk assessment. In this equation, we can see that you are going to see annual soil loss, and you can calculate it with the help of rainfall erosivity factor. Soil erodibility factor is also considered. The slope length, which is one of the most important aspects to consider if you are talking about the terrain features, crop cover factors, and the conservation practices factors. And, all these factors can be calculated using satellite remote sensing and digital elevation model, which is like the products of the satellite technology. These are the glimpses of the, the data set that are actually used to come up with the results. In the top corner, you can see the digital elevation model. This is a digital elevation model, and you can see the distribution of the, the terrain feature. This is another aspect, that is the R factor. Similarly, C factor we are seeing here, and there we are having a K factor, and then the LS factor. And based on that, if you run the model, you can very easily derive the quantitative assessment of the soil loss in that particular, watershed or basin or sub-basin, so whatever, administrative unit you want to select to calculate, the soil losses. And in this, you can see that the soil losses are calculated in terms of tons per hectare per year. And the range is from 0 to 208 in different areas. And if you can see the areas which is having more steep slopes, and also they are barren and having a soil which is having more silt, so they are contributing more to the soil loss in this particular region. You can even calculate the sediment yield in terms of tons per hectare. And this particular product is important that you can pinpoint even the location where you have to employ most of your conservation, factors, and you can also do some remedial measures. This area, and this area is contributing a lot to the overall context of the erosion in this particular area. And similarly, you can also further calculate the soil erosion severity classes. You can, distribute it as low, moderate, high, and very high. And finally, you can calculate the statistic as per different administrative unit that is available in that particular Now I'm going to present another area. This is the case study that involves the potential water site identification. And that is very successful in one of the region of Pakistan that we call Balochistan. It is vast and inaccessible terrain. They are having a limited water availability. The population is dispersed. It is highly vulnerable to climatic conditions. There is less rainfall and high chances of the flash flood due to a very, rugged terrain. 2 minutes. Okay, I will conclude. In this study, you have to calculate the catchment and drainage with the help of digital elevation model. Similarly, you can calculate the precipitation and runoff estimation with the help of the satellite data. You can calculate geology risk assessment. You can do it with the help of remote sensing, or you can use also the the geological maps for that. And then you can associate different factor based on your expertise in this particular area. You can associate different factor, and then you can calculate the overall effect. This is how we can calculate even the potential dam site. You can not only calculate only the dam site, but you can also calculate it, the wall size and the water you can hold in that, and how much area that is going to be benefited out of that particular dam. Here in this case, you can see. So in conclusion, we can very confidently say the space technology can be applied for mapping and monitoring of soil erosion with average annual soil loss, erosion intensity, and sediment yield. The information can be really helpful and a step forward towards proper planning and implementation of strategies to control the erosion and protection of the natural resources. Suitable water harvesting structures such as dam site selection with advanced hydrological analysis can be done using remote sensing technologies. Thank you very much.
Thank you, Mr. Amjad. We have 1 minute in case you have any questions. If not, remember, we have the 30-minute Q&A and discussion section. Do you have a question? Oh, please go ahead.
So I have a question. I know that it can be difficult to get information to calibrate the Russell model. Do you have any sources of using information for being able to calibrate the parameters that go in and the results from the Russell model?
Thank you very much, sir, for your question. This is a very relevant question, especially if you are doing studies at such a scale. Though in this case, we have also done some, studies at a field scale. We have conducted the whole system at a field level, and then we have done different analysis to come up with different, the factors that we have actually added to come up with the C factor, K factor, R factor, and all other factors. But, the Russell model I have chosen for a reason that this is widely applied in a lot of regions, and they are all well calibrated by one of the very good institutions, even in US and other part of the world. So if you use Russell model and if you adopt the proper methodologies and with the proper data set used, so I think that would be widely acceptable. Thank you very much, sir.
Okay, we'll move ahead to our next speaker. This is Nodira Telyeva from the Center for Space Monitoring and Geoinformation Technology in Uzbekistan, National Space Agency. And the talk will be titled "A Novel Approach for Environmental Monitoring and Policymaking." Nodira.
Hello, everyone. Good morning, dear ladies and gentlemen. And for those of you who haven't met me, I am Nodira Telyeva. I am a leading specialist in the Department of Artificial Intelligence and Development in Uzbek Space Agency. Our agency is quite young, only 3 years old. That's why international collaboration is quite important for us. And we are eager to learn and grow alongside the global space community. And I want to take this opportunity and thank everyone, organizers and everyone involved in this event, because It's really important, as I mentioned, and thank you for the opportunity. Or as we say in Uzbek, katta rahmat. Before I delve into the activities of our agency, I would love to share some information about Uzbekistan, because I'm going to be honest, I had a hard time explaining everyone where I come from. So Uzbekistan is located in the heart of Central Asia. The capital is Tashkent, and our population is around 35 million. We boast a rapidly growing economy with significant reforms underway. Uzbekistan is blessed with natural gas, gold, uranium, and cotton. We're also home to the historic Silk Road, cities of Samarkand, Bukhara, Khiva. Our official language is Uzbek. Interestingly, Uzbekistan is one of the only two doubly landlocked countries in the whole world. And this unique position offers a different perspective on environmental and economic considerations for space explorations. Now I want to draw your attention to the RLC, or at least at its remainings. This image paints a stark picture of its dramatic decline over the past years. Once a vast inland sea, the RLC shrunk to a fraction of its former size. This ecological tragedy is a stark reminder of the consequences of unsustainable resource management. The primary culprit behind this disaster is Soviet-era irrigation projects, because in an attempt to boost cotton production, vast quantities of water were diverted from Sirdarya and Amudarya rivers, and which are the RLC's main sources. The unsustainable water extraction left the sea parched, unable to replenish itself. The results? By the early 2000s, the RLC had shrunk by a shocking 90% of its size. The consequences of the RLC shrinkage have been catastrophic. The RLC once thriving fishing industry has virtually vanished, and the ecosystem has been severely disrupted. The picture you see in the background is called Graveyard of Ships. These are all fishermen ships that once were operating very effectively. Secondly, with reduced freshwater inflow, the sea salinity has skyrocketed. This has devastated surrounding agricultural lands. And lastly, toxic dust storms carrying salt and pesticides from the exposed seabed now plague nearby communities, leading to respiratory and health problems. A lot of forces have been put to try and restore the RLC. We in Uzbekistan, we also have a small joke saying that if every organization or people who came to analyze the RLC situation brought at least one bucket of water, maybe the RLC would be restored. But unfortunately, the RLC already cannot be restored. All we can do is to prevent such situations in the future. And now a little bit more about the major problems. Uzbekistan is trying to grow very rapidly, economy and industry-wise. But we are encountering a lot of ecological issues. Our economy relies heavily on agriculture, particularly cotton production. However, unsustainable irrigation practices are depleting water reserves at an alarming rate. This creates a vicious cycle as the water scarcity further hinders agricultural productivity. And also Uzbekistan is experiencing rapid urbanization, with Tashkent becoming a major metropolis. This population growth puts a strain on water resources and contributes to air pollution. A recent air quality report by IQ Air even listed Tashkent as one of the most polluted cities globally. This situation is further compounded by climate change. Current trends suggest that five-fold increase in water scarcity by 2050, and water resources in Sirdarya Basin are expected to decrease by 5%, while Amudarya by 15% by this time. And here I want to talk about a little bit more about digitalization because as we all know, it's impossible to build some data-driven solutions when we don't actually have the data. And our agency, for the past few years that it has been established, tried a lot to build up data sets so that we can later utilize it for our projects in ecology. And we have worked on the Open Data Portal, where we establish a user-friendly portal to make valuable data sets readily accessible. We mostly worked on, for example, trees and forest extraction, land extractions, land use classification, water bodies, and of course, building parcels and parcels to analyze the urbanization rates. Also, we recognize the importance of collaboration. Our portal also integrates global open source data sets like MODIS, Copernicus, and NASA data sets relevant to our region. However, data collection was just a first step. The true power lies in utilizing it and creating actionable data, as our expert already mentioned. And here I want to show you the portal we have generated on a lot of the water dams that we have in Uzbekistan. To effectively manage water resource and address the looming water crisis, we need accurate information about the actual storage capacity of our reservoirs. This data is crucial for making informed decisions about water allocation, infrastructure development, and conservation strategies. Unfortunately, current methods for assessing reservoirs often fall short. Traditional methods such as ground-based surveys are time-consuming, expensive, and limited in their spatial coverage. The lack of reliable data leads to inefficient water distribution and, in extreme cases, to water shortages. Advanced technologies like satellite monitoring and bathymetric surveys offer a promising solution. Satellite imagery provides a comprehensive view of water bodies, allowing us to track changes in water levels and identify areas of depletion. Bathymetric surveys, on the other hand, measure the depths of water bodies, creating the detailed 3D topography maps of these dams. Currently, if we look at the case study of the Charvak Reservoir, currently Uzbekistan has almost 70 plus strategically and economically significant reservoirs in Uzbekistan, 64 of which are naturally filled, increasing sedimentation levels. 25 of them have been digitized and analyzed, and you can see them on this portal. We will look at the Charvak Reservoir, a critical water source for Uzbekistan, which exemplifies the power of these strategies. Initial design estimates placed the reservoir's capacity at 2 billion cubic meters. I'm sorry, it's in Uzbek, but I think you can navigate through numbers. The first capacity was estimated at 2 billion cubic meters. However, bathymetric surveys revealed a current capacity of only 1.84 billion cubic meters, indicating a significant loss due to sedimentation. This finding has prompted measures to address sedimentation and optimize reservoir management. And recognizing the need for accessible information, the Uzbek Space Agency and in particularly our team tried to design the very interactive platform so that the decision makers and the policymakers who are not really does not have background in, for example, environment, etc., might understand the current situation. And this is really simple. We just added some interactions, like you can see how the water levels rise through time, through different seasons. And but it was also effective and very well welcomed by government organizations. So the benefits of data-driven reservoir management were, first of all, improved water allocation, infrastructure development, and conservation strategies. Okay. I also want to tell a little bit more about the disaster that happened in 2020. There was a huge Sardoba Dam disaster occurred on May when breach caused severe flooding in Sirdarya region. In order to prevent these situations, we worked a lot with interferometry and INSAR imageries to analyze the threats that are occurring around these dams so that we can further preserve them. And with that, I think I should tell a little bit more about challenges because there are a lot of them. So, of course, the first and primary one for our country must be the cost, because bathymetric analysis are really expensive, but this is something that we really need. That is why we are investing in those. Also, data management and analysis with integration for existing platforms, and not mentioning capacity building and cybersecurity issues. But looking ahead, we are looking for different direction as, for example, IoT. We want to implement hydrological stations alongside with agrometeorological stations. And in that, we are trying to cooperate with a lot of the startups in Uzbekistan that have already found their followers and the trust of people. We are in the active negotiation terms with those. And also we want to implement a lot of AI-driven suitability analysis for effective land and resource management. And of course, shift our focus also to water quality monitoring, because although we can find the water quality information from the open source resources, it's still quite hard to understand what exactly are the percentages of the water quality parameters. And also empowering collaboration with governmental organizations and startups, as I mentioned earlier. And thank you.
We have time for one quick question if somebody has a question now.
Thank you. That's a nice presentation. I would like to ask something I didn't understand very well about the flood example that you showed. How interferometry is helping you to map that kind of disaster? Because I understand that it is not so useful for water measurements.
Yeah, this one is mostly to prevent dam breaches. We analyze the displacements like horizontal, vertical, and those displacements to analyze the likelihood of dam breaches to prevent the consequences it might bring.
Okay, yes, thank you.
Thank you.
Okay, next up we have Ameria Baitu from the Ministry of Lands, Housing, and Human Settlements Development in Tanzania. The title of her presentation is Rufiji Mangrove Forest Mapping and Monitor with Space Technologies.
Good morning, everyone. I'm so delighted today to be here. It has been a long journey. Thank God I'm here today. As I've been introduced, I'm Ameria from Tanzania, East Africa. Today I'm going to present to you about the mangrove forest, concerning about the space technology, how can it be used in making better measurements, especially when you are on the ground. First of all, why we decided to use this kind of technology? We had a problem, like you see. The forest poses significant conservation challenges because it's vast and often inaccessible area. However, remote sensing can solve this problem because it offers the best solution and better understanding for protecting this ecosystem. By analyzing satellite data, we can map mangrove area track changes over time, and make informed decision-making, especially in conserving this kind of species. As you can see on your left side, this is the mangrove, how it looks like. You can see the roots, how it appears. And down here is the study area. This is Tanzania. And this is the area where I'm going to talk about, the area with a red line. The goal is to enhance our ability to safeguard these critical coastal habitats. The objective of the project is to conduct time series analysis of change in forest covering by the use of LiDAR data in Google Earth Engine. And the second objective is to create mangrove extent map using random forest classification and also mapping forest stand height of the forest. The significance of the study is there are many, but vulnerability to climate change, it can protect the habitat and the living organisms. Also, it is easier to have data since it is inaccessible concerning the structure of the forest itself. The comprehensive assessment, we can assess according to the challenges facing on the ground. And also, it is easier to build the capacity building over the person or staffs who are conserving this land. Historical background of the mangrove itself, where we can see at the map on your left-hand side. This is the area we are going to talk about that covers the delta where the mangrove forest situates. Historical background of the Rufiji Delta particularly significant as it constitutes the most important fisheries along Tanzania coastline, according to about 80% of wild shrimp catch. The Rufiji mangrove forest is situated in the Rufiji Delta, which covers about 20% of the Tanzania's land area. It consists of 5 rivers, Rufiji, Ruvuma, Rupangani, and Iwami. This is the major rivers that pours the water in this area. The total area of this delta, the forest is 53 to 55 hectares. It extends along the coastline about 1,424 kilometers from the border of the northern part of Kenya, and it borders to the southern part of the Mozambique. It is this area of mangrove, this one, and the delta is monitored by the agents called the TFS, Tanzania Forest Reserve Service Agents, under the Ministry of Natural Resources and Tourism since 1928. Also, you can see here, because the area is very large, it covers 14 administrative districts. Therefore, the mangrove forest counters so many challenges, as you can see. The first one is degradation and conservation because of different activities run by the people residing in the area. And also, the land tend to change because of the need. Others tend to do it in a cultivation land, and others tend to put it into they cut trees for charcoal, others for logs. And another challenge is climate change, where the sea level rise because of climatic change. That can cause temperature also to rise and make difficult for living organisms. Also, the encroachment of the area. Most of the people tend to encroach for paddy cultivation, sometimes for poachers, because it has a lot of type of animals. And oil spills can tend to destroy the living organisms. As you can see on your left side, you can see this one is one type of the mangrove tree. You can see the roots, it is finger-like. It makes easier and better for habitat with the living organisms or the fish or other biodiversities. It has importance. The first one is to absorb impact of waves and protect the coastal area from storm and rising the seas, and sometimes when it happens, the hurricanes. The second one, it absorbs and store carbon annual where there is a car, especially in urban, near the urbanization. Also, the biodiversity of mangroves tend to be a better area for habitats, and also can be used as a timber for construction. It is the source of energy and also the food and medicine. It controls the pollution. The methodology of this project was, like I said earlier, it was 3. The first one, time series analysis, where I supposed to visualize the satellite data. I used the satellite one. I selected the area of interest with the coverage. After loading, I just picked the time I wanted, because I wanted to make a time series analysis. Like you see here, I chose 2026, 2020, 2022, and 2023. Then I applied the thresholds because before analyzing, you need to convert it from the complex method to be simpler in order to be interpreted by other data. So I converted into GeoTIFF. Therefore, we compare the vegetation loss and forest cover change over the time. And the methodology of the second one, of the extent map, is setting up the map on Google Earth. We filter the Landsat, constructed a random forest model and time series comparison, and thereafter, the new random forest can be created. We calculate the mangrove area to see if there is a changes, and also export the layer of interest into other software in order to be readable. And finally, we tested the accuracy of the data. So we assessed the accuracy by the plugin called Access plugin. The software I use is Snap, first of all, for thresholds, and Google Earth Engine, and QGIS for assessment. So you can see the result of vegetation loss between 2 time series. In here, you can see the result of 2020 and 2022. And comparing with 2022 and 2023, you can see the difference from the first one and the last one. Even the graph, after processing, there is a graph, you have a graph, then you can export it into document and other data to be shared. So we had to see the extent of the mangrove and access the accuracy of the data. Remember, we need to have a percent. If it is 0%, if it is 100%, so you interpret your data according to your result in order to see the accuracy of it. So as you can see, we had an area earlier, if I showed before, it was a 53 to 25 hectares. As you can see here, it is 48,030 hectares. You can see the difference from 53 and now is 48,000. So the results interprets that the area measured by manual method or traditional way compared to the space technology method it has a difference because it is inaccessible and it has a lot of vegetation. So there is area also which is not covered by forest or whatever mangrove forest. Therefore, in a manual way, you can never even detect, but the space technology can detect it by the use of satellite imagery. Therefore, if you want to access the class accuracy plugin, you can see the link over there. The conclusion is to invest in scientific research in order to protect this mangrove, the remote sensing to be used in monitoring, also to engage the community in order to protect these important species, and also strengthen the legal protection to avoid these poachers, whatever, and international cooperation also needed for better practice. As you can see here on your right, on your left-hand side, this is one of the initiative, this one, for rangers and the staffs who are maintaining, and also for tourism. Thank you for your time.
So we have 2 minutes for questions. Are there any questions?
First, nice presentation. It was really good.
Thank you.
You talk about this plugin to measure accuracy in quantum sheets. I wanted to ask if you could get uncertainty data for the area estimations with that plugin, if that's something you are planning to do, like being able to say, okay, I got 480 hectares, but I know the uncertainty on that from my validation. Thank you.
Thank you for your question. The essence was to test first on the table. Then if you want to validate, you go to the field to verify, because you'll be having the areas where there is no forest on your image, the one you analyzed. Therefore, when you go to the field, you will find that this area, it can show like it is a bare land. So you confirm if it is a bare land. Now you see that the space technology is better than the traditional method. Thank you.
I guess we can do one more really quickly. Yes, sir.
This is Mandira. A very good morning. Thank you very much for an interesting presentation. Mangroves indeed, because for the Hindu Kush Himalayan region, for the Ganges Delta, this is also quite important and relevant. My question is regarding the last part of your presentation where you talk about the differences and in terms of the validation. So I see that there was about 5,000 hectares a difference change between the time that you measured 2000 to 22-23. So has that resulted in some kind of action or any kind of policy decisions in terms of the actions that's required to better preserve or conserve these mangroves?
Thank you. In Tanzania, we have many areas having this kind of species. We have in Zanzibar, Pemba and Unguja. We have it in Mafia. We have it in Pangani. So the effort has been taken care of, and it has been preserved and conserved. And many projects has been going on. And the last one has been launched in last year, October, by UN, funded by UNDP, to verify and validate this kind of process. Thank you.
Thank you again, Amaria, for that great presentation. So our next presentation is online, and we want to welcome Tehendra Kandal from the University of Virginia. And so we'll turn the time over to him. He'll be speaking about a comparative hydrological dynamics and water security in the Sudandari Hall watershed. a rhesus modeling approach for broadleaf and conifer forest. Go ahead, Tandra.
Am I audible and is my screen visible?
Yes, we can hear you.
Okay. Thank you, moderator. Good morning and good afternoon, everybody. I am Tejendra Kandal from Nepal, currently doing a PhD in hydrology at University of Virginia under Dr. Larry Band's supervision. I feel fortunate enough to be a presenter at this big events, and I am thankful to all the organizers who gave me this opportunity. And I am also grateful to all the speakers and participants for sharing your precious time. And in this session, I would like to focus on comparative hydrological dynamics and water security in Sundarjal watershed, resource modeling approach for broadleaf and conifer forest. Okay, I'm going to start with problems. The study area has been adversely affected by deforestation due to the local demands for land and resources. This reduction in forest cover has led to serious water security challenges for nearby communities in the Kathmandu Valley. In response, understanding the dynamics of forest cover, including the growth patterns of different types of forest, such as conifer and broadleaf, is crucial. Our study is driven by two main research questions. First, how does restoring forest cover impact water security in the watershed? And the second one is, what significant differences in hydrological dynamics emerge when comparing the scenarios of broadleaf and conifer forests using the RESIS model? And the objectives of this research are to assess how an increase in forest cover, either naturally or planted, influence water availability, focusing mainly on alleviating spring water and stream flow scarcity, and also looking at the flood potential from 1998 to 2017. Additionally, to analyze the ecological recovery of the area, exploring how different forest growth patterns affect the watershed hydrology by using the RESIS model. Nepal has a diverse landscape, ranging from lowlands to high mountains, which presents unique challenges and opportunities. The red highlighted is the Kathmandu district, which is the most populated district, and which one is the capital of Nepal. And my study area is Sundarjal watershed, situated north of Kathmandu district, which covers an area of 29 square kilometers, has an elevation range between 1400 to 2700 meters from mean sea level, and serve as a critical water source for the region. Previously, this area was heavily deforested, but later it was designated as a protected area with reforestation operations underway to solve water scarcity issues in the Kathmandu. Comparing satellite images before and after 2000, we see significant changes in the forest cover. The figure on the left shows that the area had less forest cover and possibly lower tree density before 2000. In contrast, the figure on the right shows an increase in forest cover as well as tree density in the year 2020. We choose this area for our study because it has undergone noticeable change in the forest cover. It offers better data availability than other watersheds in Nepal. Its size is manageable within the capabilities of our research model. And also, I presume little research has been done in this area related to the forest hydrology. We use NASA SRTM data, which provides detailed elevation information. This elevation information helps us to extract hydrological variables like watershed basin, hill slope, stream network, wetness index, etc. The global 30-meter land cover product created using Landsat imagery and the continuous change detection method on Google Earth Engine platform offers a fine classification system from 1985 to 2022. It includes 35 land cover categories, but our study area mainly consists of 15 different land classes, mostly forest. For the soil in our small watershed area, we selected homogeneous silty loam based on a soil grid 250-meter resolution data provided by International Soil Reference and Information Center, as known as ISRIC. We utilize daily time series data on precipitation, river discharge, maximum temperature and minimum temperature from 1998 to 2017 from the Department of Hydrology and Meteorology, Nepal. This is the overview of RESIS model. This model is the process-based hydroecological model. It stands for Regional Hydroecological Simulation System and is a tool for eco-hydrological simulation. It uses landscape information such as elevation, land use, and soil types, as well as climate time series data. This model simulates several environmental processes, allowing us to better understand how water, carbon, and nutrients travel through watershed. The research model includes various processes related to the canopy, meteorology, and hydrology. Canopy processes involves interaction with the forest canopy, such as photosynthesis, evapotranspiration, and interception of rainfall by vegetation. Meteorological processes accounts for weather conditions, including temperature, precipitation, and solar radiation, which influence ecosystem dynamics. Hydrologic processes simulate water movement within the landscape, including infiltration into the soil, runoff, and groundwater flow. These processes interact to simulate the complex dynamics of ecosystem and hydrological system in watersheds. It generates two types of outputs. One shows how variables change over time, while other defines the location and level of presence of these variables in the landscape. This is the preliminary results of my research. The graph represents data from 1998 to 2017, showing model-generated stream flow and observed precipitation. The simulated stream flow is represented by a red color on the left y-axis, while the observed precipitation is represented by a blue color on the right y-axis, which is inverted. Analyzing the data, we notice a decreasing trend in stream flow, especially after 2003. This decline could be influenced by lower rainfall, particularly during the dry years 2005, 6, and 2009 in Nepal, which were the part of series of weak monsoon seasons. Additionally, the designation of this area as a protected area lead to extensive tree planting, which could also impact the stream flow patterns. And after 2010, there was a slightly increasing trend in stream flow, which might be related to the higher precipitation after the year 2010 and also might be related to the growth of naturally occurring broadleaf forest. Because broadleaf forests generally use less water than conifer forests, contributing to the stream flow dynamics. In comparing the simulated versus observed stream flow, we obtain an NSC value of 0.52. In this analysis, red represents the observed stream flow, while the blue represents the simulated stream flow. Particularly during very dry periods, the simulated stream flow tends to be slightly overpredicted, especially at low flows, but the overprediction is small. This overprediction might be attributed to the limitation in the observed data or use of the water directly from watershed for drinking purposes, or might be attributed to the use of the water directly from watershed for the small hydropower located near the watershed area. At the high flows, the simulated stream flow are sometimes underpredicted, but this underprediction is also minimal. Despite these small discrepancies, the overall fit of the data is quite good. So to better understand how different type of forests affect water uses, I conducted a detailed comparison of stream flow between broadleaf and conifer forest. I simulated two scenarios, one where the entire forest was converted to the broadleaf and another where it was converted to the conifer to observe changes in stream flow. This plot shows stream flow for two scenarios. The red line represents a broadleaf forest which generates higher stream flow throughout all periods compared to the green line, which represents the stream flow of a conifer forest. And this graph is for a specific year, 2004, only to see the difference clearly. Higher stream flow from broadleaf forest would be the crucial for enhancing spring water availability. This graph further illustrates the difference in daily stream flow between broadleaf and conifer forest over our study period from 1998 to 2017. And finally, this graph represents the yearly difference in stream flow from the watershed over the given period of time. Analyzing the data, we found a significant total difference of nearly 7,500 millimeters in stream flow. This is equivalent to an annual water loss of 11 million cubic meters, impacting the overall water security of the region. So the question is, where is all the water going? To answer the question, to find the answer, we plotted two different graphs for two different forest types. In both graphs, the red color represents the broadleaf forest and the green color represents the conifer forest. When we look at the graphs, we found that the conifer forest uses more groundwater and produce more evapotranspiration, leading to more water loss from the watershed basin. So these are the location-based output displaying groundwater table depths measured in millimeter during the pre-monsoon season of 2006. The left image represents the conifer forest and the right image represents the broadleaf forest. The color bars indicate depth, with blue representing the shallowest depth, starting from 0 millimeter, green indicating a higher depth, and yellow is the highest. Comparing the pre-monsoon seasons, although they are difficult to discern, there is some different. These output are for the monsoon season, which we can easily see the differences in the monsoon season. There appears to be a more yellow in the conifer forest and bluer in the broadleaf forest, suggesting that the broadleaf forest recharges more groundwater. Similarly, these are the base level output for evapotranspiration during the pre-monsoon seasons. Upon looking at color bars, the conifer forest extends up to 7 millimeter, while the broadleaf forest only reaches up to 5 millimeters. Despite the different ranges, it is evident that the conifer forest represented by the light green experience more evapotranspiration. For the monsoon season as well, there is a notable difference in evapotranspiration rate. The conifer forest transpire more, thereby reducing the green water available in the watershed. So we found that broadleaf forests play a crucial role in mitigating downstream water challenges by using less water compared to the conifer forest. However, our analysis faced several challenges. They are low resolution soil data, limited observed data, lack of comprehensive study about the tree phenology and soil, missing observed precipitation and temperature data. So our future research will focus on these limitations to improve the accuracy of the model. Overall, our study results are important for improving our knowledge, making better policies, and using practices that protect water and environment in the higher Himalayan regions. So in conclusion, our study of Sundarajal watersheds suggests that broadleaf forests are potentially more effective at improving water security compared to the conifer forest. They appears to be better at providing more stream flow, that is freshwater flows, which benefits downstream communities. We recommend decision makers to focus on broadleaf forest in reforestation efforts, especially in the areas suitable for both type of forest, to help mitigate water scarcity challenges in the Nepal's hilly region. Finally, this research concludes that the space-based technology are crucial for sustainable water management. So these are my references, and yeah, thank you so much for your time. I'm happy to answer any questions.
Thank you, Tehendra. We have time for a couple of questions if there are questions for Tehendra. Well, I will ask you a question then, Tehendra. I'm curious to know again if what kind of information that you had available for the calibration of your model. Were these stream flow observations? And how are you able to obtain that information in order to be able to provide the calibration?
Oh, those stream flow data are provided by the Department of the Hydrology and Meteorology, and then there is a couple of there are 2 stations measuring the stream flow. And then for the calibration of the research model, we calibrated the research model using the lateral and vertical soil hydraulics properties. Other soil properties such as pore size index and air entry pressure, along with groundwater characteristics. These parameters were systematically adjusted based on historical climate data, stream flow records, and land cover changes from 1998 to 2017, ensuring that the model output closely matches the observed local conditions.
Very good. And I'm also curious if this results, how easy it is it to suggest or move towards broadleaf forest and as a management process? Are there programs involved, or how does the decision-making process go?
Yeah, thank you so much. That's a really good question. Actually, this area is in the buffer zone. I guess this area lies inside the Shivapuri Nagarjuna National Park, and then this area is a buffer zone community forest. And then the community can manage the forest of this area, and then we found that this area is suitable for both type of broadleaf and conifer forest. So if the conifer forest uses more green water, then it will result in generating the less stream flow. So if the area is capable of having both type of forests, then the community can, I think if the policymaker make some type of decision, then the communities people can implement the plantation of broadleaf forest rather than the conifer forest.
Okay. One more question here from a native Nepali.
Yes. Hello, Tejendra. This is Mandira. I'm also from Kathmandu, from Isimod. So thank you for a very nice presentation indeed. Good to hear about some of the insights of the Sundarijal watershed that's in Kathmandu. You mentioned that you're using the RESUS model. So I was wondering why RESUS model? There are other various different types of models also available. So what was the choice of the model, and should the different model be used? Would you see any changes in your results? Would that be anticipated?
Thank you so much. And then, hello, Mandira ma'am, namaste. I'm so happy to see you there representing our beautiful country, Nepal. And the question you asked is really good question. Actually, the RESUS model is a type of eco-hydrological model where we can simulate not only the water flows in the watershed, but we can also simulate the carbon and nutrients flow inside the watershed. Actually, this time, this is our preliminary results, and then we are looking at the water and stream flow only. And later, we are planning to generate the results for the denitrification and all the nutrients flow, and then how the carbon changes over the period of time. And then I can use a different type of model, like as we are still practicing to use the SWOT plus and then a QSWOT model in this watershed. And then we are also planning to look how the results from the RESUS model and then the SWOT model will vary if we do some type of results in that watershed.
Okay, thank you once again, Tejendra, for joining us and for that excellent presentation.
Thank you so much.
I was recently informed that PodMe canceled, so we have about 10 minutes, let me check, about 10 minutes for additional questions or comments that you have for our presenters. Are there any questions or comments for our presenters? Yes, please go ahead. Can you have the mic?
Yes, thank you. I have a question for Mr. Nelson, because you mentioned the need to have early system mechanism, early warning mechanism in place, especially in the event of the flood in Darna in Libya. So I would like to know how GeoGlow is actually making the link until this early warning mechanism are implemented. Thank you.
Well, thank you. And of course, the most important link there is the community and the local community. Like I mentioned, in the case of Libya, where the information exists, but the people, the local area do not either know that it exists or do not know how to use it. And so in the case of GeoGlows, and I already mentioned one of the projects we've been involved with is the NASA Severe program. Severe has hubs in 5 different regions of the world where there are local expertise and where they're familiar with the agencies, the disaster management agencies, the hydrometeorological services, those who are responsible for having the information and then being able to communicate and make decisions. And so that has been our primary mechanism to date, is working through NASA Severe with local stakeholders. Mandira, as I mentioned, comes from Isimod, which is the hub in South Asia that's responsible for helping local agencies to understand and use them. And I think that's the critical piece of all of these kinds of technologies that we're talking about. They are available, but how do people learn to understand them and then gain confidence in their use? And that is a large task. And again, part of the United Nations Early Warnings for All aspiration is to get beyond the science that we're developing to have impact. And it begins with understanding that we don't, as scientists, we don't have perfect solutions. We understand the limitations, and yet we have models, we have the ability to provide adequate information that's reliable for making decisions with, as I mentioned, with the example of Google Earth, the expectation that these are going to improve through time, and that then there will be benefits because we'll know how to use them, we'll know how to deploy them, and they'll be integrated in our decision-making and policy-making processes.
Sir, my question is about the flash flood. Do you have any reflection of flash flood in the current system, or you're looking for any such type of arrangement for any future in the GeoGlobe?
Yeah, I would say that the current system lacks somewhat the mechanism for flash flooding. However, when there's indicated potential for flooding over the medium range, the 3 to 10 day period, it generally is indicating hotspots where there are potential for flash flooding, but the the meteorological forcings and hydrological model is not at the resolution that tends to detect the very sudden rise and flash flooding that occurs over smaller areas. And that's why I mentioned organizations like in El Salvador, Marne, in South Asia, they have a higher intensity, high impact weather meteorological models. And in some of those locations, we are adapting those to the system where they exist so that we can provide a better local flash flood warning. Other questions or discussions in general about the technologies and the things that we've learned in this session?
Thanks, Dr. Nelson. Karthi from International Water Management Institute in Sri Lanka. And I've been following TETSIS and for almost like 7 or 8 years, because I myself was briefly part of a survey Mekong in Bangkok from the SEI side. So the question I have is, like, now you have this platform, and you also know about the Google flood forecasting platforms, and then you also have a number of regional platforms which are probably having very similar, not exactly the same, but similar type of outputs. How do you foresee the convergence of these platforms in the coming years or days? And just a second follow-up question regarding the TETSIS is, are there any examples of uptake of this TETSIS package by private companies and adopting it for developing geospatial applications? Thank you.
That's a lot to unpack on those questions, but I think that ideally the local modeling and regional platforms are best served because, as I mentioned, that local expertise and understanding is required and needed. But I do see my experience over many years in hydrological modeling is it's very difficult to maintain and sustain as technologies change and capacity, all of the requirements to keep a local system running and operational. And so that's where we hope that GeoGlows can kind of fill those gaps, provide a foundation so that in areas where they don't have that capacity or able to sustain it, they have a baseline solution. But I do feel strongly that to the degree that capacity exists, there should be these kinds of local models and adaptations that can inform better those processes. But that has been a very difficult thing as we large investments have been made in infrastructure and capacity building. And then next year, the technologies change. And all of that's required to be propagated, and all of those systems then need to be updated. And that's why things like Google Earth Engine are so powerful, because they are improving those technology, the information that's there. And as you become able to use that information, you're able to more quickly adapt to the innovation and the new products that come along. And so it's a difficult process, but I really do see it, like I mentioned with that Google Earth example, that it may not be as adequate or as good as you want right now, but it's going to continue to improve. With respect to your second question, example of there are private companies using it. We don't have those documented nearly as much. There is a website, stories.geoglows.org, that lists several different examples, but they don't tend to include private companies, though there are many studies where they're using this information in order to do their analysis and have the baseline hydrology.
We have some questions for Jim Nelson from the virtual audience. What are some of the main challenges that GeoGlows face to improve global collaboration? And what is the feedback you have for decision makers?
Yeah, I would say one of the main challenges we've had is that it's really hard for any one organization to own a global system. And so, for example, we developed from the United States National Water Center, the original model, but it's driven by the Europeans' forecasting system. So the United States felt like, well, this is not our model. Similarly, because we belong in the United States and are researchers from that organization, in the European, we're not funded or supported necessarily because we're not European and we're not part of the European Union. But the cost, the benefit, I would say, of what we're doing is tremendous over everywhere, but no one person owns it, or there's an organization that way. And so that has been the biggest challenge. However, working with the World Bank, working with the World Meteorological Organization and other United Nations organizations like here today, they are looking out across the whole aspect and have helped provide the glue, if you will, for these organizations that support us in terms of developing a global collaboration and doing it.
Thank you.
Mandira?
Well, just adding on to the questions that were asked, but more in terms of a response from like one of the users or collaborators. Like was said by Professor Nelson, definitely this GeoGlows has been adapted for the rivers of the Hindu Kush Himalayan region. And earlier there was a question whether that could be done on a regional level. And so this is an example where there you have a regional product that expand through three large river basins, the Indus, the Ganges, as well as the Brahmaputra. And then what is important here to also take note of is that it can be customized for the region of interest, but also looking at it at the country level. So the more data, the local data, the in situ data that you have, and then working with the experts to further refine some of those to have better predictions, better estimation. That's one of the ways that you can work, is the provision of your data and information to provide for the validation, but also equally to calibrate the model better and have better outputs. So that's one of the ways that can also be looked into, the collaboration for improving the outputs that you see for a particular river system, and to look into the forecasts. But another question regarding the flash floods that came. Yes, definitely. The one that Professor Nelson just presented is for mainly for larger river systems, stream flows, like he said, with a larger kind of lead time of 10 days of forecast or predictions. But looking at more the flashy rivers and flash floods, he mentioned about this high watt system that we have at also ISIMOD running. That's the high impact weather assessment tool, where you're looking at numerical weather predictions and then using that input into another model for flash floods. So that can be customized in that sense to have flash flood outputs. But also just wanted to remind that there are other tools like the flash flood guidance system that is being operated by the World Meteorological Organization, but again, customized for each of the regions. That's also available. So yes, there are many different products and tools that are available when it comes to flood prediction, flood estimation, let's say forecast better. And it is also up to the users then to, see how best those outputs are and then make the appropriate decisions. So one model is not, does not give you all. You have to look at a suite of model results to make your decisions. Yeah, thank you.
Thank you. I think we're at the moment for our break. We're going to take a 30-minute break. But we have time at the end of this session for further discussion and questions. So be thinking about the questions that we might want to ask. And I'll just end by also suggesting with models, I always say that all models are bad, some are useful. So no model is perfect, I guess is what I want to say, but the one that's best is the one that you know how to use, that you have invested and calibrated and understand. And so I think that's an important thing to always remember in our modeling. So let's go ahead and take a break.
Yes.
Oh, 20 minutes.
Yeah,
right?
so we have close to 20 minutes until 11. We will reconvene at 11. Okay? We'll break now.
And sit down again. We're about ready to start. Let's just take a couple more minutes and then we'll make up the time when the discussion at the end. We will probably won't need full 30 minutes. We won't have 30 minutes, but we can invite everybody back in.
Alex says that he will probably take 15 minutes for his presentation, which is okay because we have a Q&A.
So then no questions after?
Exactly. Okay. So we have, after Alex, we have one more presentation and then we have a space for the Q&A.
Okay. Let's go ahead and begin. Continue our session here on space technologies for monitoring forest watersheds and their interplay. And our next speaker, we have two more talks, then a little bit more time for discussion before our lunch break. And so our next speaker is Alexandre de Amorim Teixeira. He's a GIS specialist from the Brazilian National Water and Sanitation Agency, ANA. And he'll be speaking to us on integrating hydrographic intelligence in spatial databases, the innovation and global application of PG Hydro. So let's welcome Alexandre, and we look forward to his presentation.
Okay. Good morning. Thank you very much for being here. It's a great opportunity to share our experience that we have dealing with water resource management in Brazil. It's a congratulations to all the organizers for this great event. It's very good to see how interesting and how different. And I should say that the diversity is the mother of the creativity. So I'm just having a lot of insights in this event. Thank you very much. So the National Water Agency of Brazil is responsible for the water resource management because we have the water resources policies, and we ensure that water resources policies ensure that it's being followed. So one of the main reports that we have in Brazil related to water resources is the Brazilian Water Resources Report. And it's interesting because we just collected all of the information that we need for water availability, water use, and so we can calculate the water budget. So that's we can plan and organize all our resources applied to water. So I'll present for you now. It's the integration. It's the hydrography database that we use in Brazil, and we start in 2004 when database and spatial data was a problem for us because it didn't have any. So, but today we still have a problem because now we have a lot of data to deal and to process of this information and to present with, to help people to guide in water resources management. So in the first, when we are dealing with our first hydrography data set, it was built in 2004, and we have more than 100,000 drainage lines in Brazil. And associated to it, we have a drainage area. But at that time, we used the GIS tools to process all this information. And yes, we worked with ArcView 3.2. I don't know if you worked with this GIS. I'm just saying how old I am here. So we, in 2007, we migrated to ArcGIS, but in the end, we didn't could process all this information that we had because we have plenty of that. And plenty of this information, it was 200,000. So by now we have a hydrography data set that we just have more than 5 million drainage lines in drainage areas. So we have to change our methodology to process all this information. Basically, for our hydrography data set, we have drainage lines, we have drainage areas. For each one drainage lines, we have one drainage area. And we process all this information, and we have a lot of information pre-processed, saying, for example, what's the drainage area that you have upstream. We have the distance to the sea. We have the other information that help us on water resources management. So to process all this information, we have to change the technology from a GIS to a spatial database system. We use the PostgreSQL with PostGIS, and we developed an extension to it. The name is PGHydro. And we use the QGIS to view this information to use like a GUI to process all this information. So to extract the drainage areas, we used a software called TerraHydro, and used some other codes to process this information. But by now, we just use TerraHydro. I really suggest that you take a look on it because we extracted all this information using the digital elevation model, and we have one drainage area for each one drainage lines. So our one thing that was very important was how if the software was able to process all the information that it had for Brazil, because as you know, Brazil is very large, we have a lot of data to process. And so to running each one of these processes, TerraHydro just processed the information from using NASA, for example, for the entire South America. So yes, we just have to try to process the information for a huge amount of data. So basically, we just extracted the drainage areas for each one drainage lines that we acquired from the cartography data set. Here is a summary of this process. Just get the digital elevation model, and we extract the information for each one of these drainage lines. Here is a GUI in QGIS. We are just presented here how we do that using the TerraHydro. The TerraHydro like a plugin using in QGIS, but it's standalone. You can use it just using a command line in Windows, for example, but you can use this GUI to help you to do something like that. And here is an example of each one of these drainage areas that we extracted from each one of the drainage lines. So we developed this GUI. It's an extension to QGIS. The name is PGHydro Tools because the PGHydro itself, the extension, it's all the intelligence is in the spatial database system, okay? And we just use the QGIS like a GUI to process all this information. So using that, you can process all this data. One thing that's interesting that we can make the consistency of the drainage lines to make sure that all the drainage lines are connected. We don't have loops. And yes, 5 million drainage lines are all connected for Brazil and some for the rest of the South America. And we make sure that we have one drainage line for each one drainage areas, so we can extract and process all the information that we needed. So here is the South America, it's the digital elevation model for South America. And here is a zoom where we can see the drainage lines. And for each one of these drainage lines, we have a drainage areas. As you can see here in the left, you can see the layers that we use. You have a drainage line, you have a drainage points. The drainage points are the nodes of this hydrography data set and the drainage areas as well. So you can identify which one is the source of the drainage lines, for example, the confluences and the outlet, for example. And related to each one of these drainage lines, to each one of these drainage areas, you have a lot of pre-processed information that can help on water resources decision-making. You have the FAFSTAT basin code, we have the reach length, water course length, drainage areas, upstream drainage areas, the distance to the sea, distance to the basin outlet, drainage line flow direction, upstream reach, downstream reach, conversion reach, water course order, installer order, FAFSTAT basin level, and FAFSTAT water course level as well. So comparing here for the previous database that we had, we came from 100,000 drainage lines to now we are dealing with more than 5,000 drainage lines. One thing it's very interesting that we just use this data set to make some aggregation, and doing that, we can maintain the topology from the drainage lines and drainage areas, but in a more homogeneous density of drainage, for example. As you know, because this data set, so we have this for example, because this data set, it's a multi-scale, have different resolutions on it. And to present the information in a national scale, it's important that everything should be homogeneous, because by other side, we just have a distortion, have a distortion in how the national information are presented. So the main advantage of FAFSTAT system is that you use a natural and hierarchical method based on topography in the drainage area. Drainage system topology can be identified through the digit codes. Yes, we can do that. And easily implemented by computer program as well as a geographic information system. So here it is. Here is why, for example, that you have the FAFSTAT basin code system is so popular in the world, because you just can use a simple select that you can use in a GIS, and using this specific formula equation, you can select everybody that is upstream. It's very easy. We already had the relation arc node, but using the SQL, we can just select everything that we have upstream. So it's very interesting, because basically for water resource management, you just have to know what to have upstream, not to have downstream. So advantages using PG Hydro is that we have a fast processing for large volumes of data. We have the vision of data processing using native DBMS tools. It's totally open source, and you can use your defined data output with no need for partial or total duplication of data. PG Hydro is available on the GitHub. You can download it if you want. If you can, as it is in the GitHub, you are able to contribute with the code as well. Here is the PG Hydro extension plugin that you can download using the QGIS. We have a tutorial showing how to construct any hydrography data set as soon as you have the drainage lines and you have the drainage areas as well. And Outlook, we have here, we are working not only with vector data, but we are working with a hybrid data set, because we can use inside the PostgreSQL, PostGIS information vector, in vector file, vector format, and the raster data as well. Thank you very much. This is the presentation.
I need to apologize to Alexandre. We got the 2-minute warning a little early, so there is a little bit more time, and I apologize for rushing you through. I don't know if you want to
No, but I didn't gonna rush with
Okay,
that. It
all
was
right.
just fine.
We have time then for a question or two for Alexandre, if there are questions.
Thank you, Alex. I just wanted to know which dam do you use?
Okay. As since 2004, we evolved with the availability of the dams that we have. So we had our SRTM with 90 meters. After that, we worked with SRTM with 30 meters, NASA dam as well, because it's a multi-scale, right? But by now, we are working with ANADEM. ANADEM is a digital elevation model that we produced there at the agency together with a university in the south of Brazil. We just used the Copernicus dam, okay? We used the ISAT information, JEDI information, and Sentinel to identify all the vegetation, okay? And we used render forest machine learning to extract this information or this vegetation bias. So now we have it's available for everyone, not only the data, but the process that we processed that. So we are applying ANADEM by now. We released this new, the 1.0 version in March. So it's very new. It should be great if you have a feedback from you if you wish to use it. But the comparison with other models, we are very happy and very excited with the usage of it because just extracting the vegetation, it's not a MDT, right? It's not a DTM, it's a pseudo DTM, right? But we extract the information from it, for example, the flow direction, flow accumulation, and the synthetic drainage as well, and compared it to the Copernicus dam, for example, that's the original one, it's improved a lot. So we are very excited with this product.
Very interesting. Thank you.
Thanks so much for such an interesting presentation. So since you're working with drainage, you have worked with neighboring countries as well. I'm not sure from one of your images, because for example, in the boundaries with Bolivia, the rivers are born in the Andes and go down until your country. So what was the spatial extent of your networks?
Good question. For Brazil, for example, we just take the best drainage lines originated from the cartography that we had. So the lower resolution that we have for Brazil is 1 to 250,000. It's almost for the Amazon region. We have this scale. And until, for example, for Brasilia, where I live, it's 1 to 10,000, for example. But for the Amazon watershed, for example, in the countries that make that is neighbor from Brazil, we just used the drainage, synthetic drainages from another project that's the Hydro 1K. It's 5 million. The scale is of 5 million, okay? And we integrated all the rivers in the South America according to the Fafstetter code system. And so we just have in the level 2, the main drainage lines and the main watersheds that we have. But it's multi-scale. So for example, for Bolivia, Peru, if you are interested to integrate this information together with us, it's completely possible to take the information that you have from the drainage lines, for example, and extract the drainage areas for each one of these drainage lines. And we can integrate with this information for entire South America, for example. It's totally possible to do something like that because we did that along with the years because it was impossible to do this more than 5 million drainage lines if we didn't have the help from the states, okay? Because we have 27 states in Brazil and we developed this technology, we transferred this technology to the states and the states built this hydrography data set. Together with them, we just included this in this scale data set. Thank you.
Okay, so we will now proceed with our last presentation and then move to our 20-minute Q&A discussion period. So next up is Harriet Okal from the Stockholm Environment Institute in Kenya, and her presentation is titled Assessing Era 5 Land Performance for Hydrological Modeling in Data-Scarce Sub-Saharan Africa Regions. Go ahead, Harriet. Thank you.
Thank you so much and greetings everybody. It's now 9 p.m. here in Nairobi, so a warm greetings to you. My name is Harriet, as I have been introduced, and I'm presenting part of my PhD work, and my PhD is focusing on integrating satellite data in reducing hydrological modeling uncertainty for water resource management in sub-Saharan Africa. But for the purpose of this presentation, I will present one of my objectives, which is assessing Era 5 land performance in hydrological modeling in data-scarce regions of sub-Saharan Africa. Just a quick background, hydrology is a vast field that has different subjects, including hydrological modeling, ecohydrology, water resource management, you name it. But in all this, there are two key fundamental factors, which are, which are human expertise and data and information system. So these two factors are most often overlooked, but they form the foundation of my PhD. So in the Hydrological Modeling Society of Africa, we are faced by a couple of threats for example, we have data scarcity, information reliability, and local capacity. So these three form the biggest threats to sustainable water resources assessment in sub-Saharan Africa. But of course, as we all know, for any successful application for a hydrological model, we of course need expertise and some data to assess the validity of model outputs as well as the inherent uncertainties. But in most parts of the region, both of these are lacking. Therefore, we find it quite difficult to find necessary resources in setting up useful local hydrological model. Therefore, you find that most studies opt for global hydrological models. But what is the best way forward? Should we continue using global datasets and hydrological model outputs, or should we develop capacity in the region to set up and run local hydrological models? Well, the answer is clear. It's supposed to be true. But as a PhD student, I can't develop capacity using one thesis. So my research tries to reduce the uncertainties that come with the first option. My thesis objective or aim is to use regional constraints to facilitate the setting up of hydrological models in data-scarce regions of sub-Saharan Africa and reduce uncertainties in modeling by proposing a remotely sensed product with reliable hydrological data and outputs. But for the purpose of this presentation, the specific objective is to assess the capability of Era 5 land in producing regional constraints in data-scarce regions of sub-Saharan Africa. So how did we come about this? To achieve the objective, there is a number of steps that I took. The first was an intensive systematic literature review, where we did a web search on all available remotely sensed products that cover Africa, and then described these products and came up with a catalog of the remotely sensed products. Then, as you can see, we are here, and let me just put my pointer. We are here, where we are justifying the use of Era 5 land. And to do this, I downloaded the data using the Google Earth Engine platform and uploaded different shapefiles for the different regions that of interest, and downloaded the data from the inception of Era 5 land, which is from 1950 to 2023. But then when it comes to Eswatini, I downloaded the Era 5 land data using the overlapping period of 1950 to 2012, and 2012 is corresponding to the observed data on the ground, which is from the WR 2012, which we term as the most hydrologically sound in situ data in the Southern African region. Then as I downloaded the data, the RFI land, I downloaded the daily data first and then aggregated it into monthly and then input all this data into the SpartSim framework where I generated constraints for both the WR 2012 as well as the RFI land. And the constraints of interest were the aridity index, the mean monthly runoff, the 10th percentile, the 50th and the 90th percentile, as well as the percentage of zero flow. And of course, I didn't do this only for Eswatini. I went beyond Eswatini, but for the purpose of this presentation, I'll give you the results of Eswatini. Thankfully, I'm presenting on the very last day, of which many of you have had RFI land, so I will not go deep into discussing what it is, how it operates. So I'll just go to the next slide to show that RFI land has been applied widely in sub-Saharan Africa for agriculture, disaster management, as well as climatic studies. Well, I will also not go deep into how the data space looks like for RFI, but I'll just mention that we can access it online, of course. And also the advantage of RFI land is that they store their data in an international data center, ensuring a reliable and secure data storage for long-term use. And also they provide us with visualization tools for easy analysis and interpretation of data. The reason why we chose RFI land is there's a lot of reasons. First, they provide multi-variable information, meaning that we do not have to go and look for precipitation somewhere, go look for evapotranspiration data somewhere, soil moisture from somewhere. It's all under one roof when we are looking at RFI land. And they provide the most basic input data for any hydrological model. And of course, it has a higher resolution than most of the products that we looked at. And it gives multiple time frames. So depending on the hydrological model that you're using, whether it's hourly, daily, or monthly time step, we can have it, RFI land can give you that data. And of course, it has been validated and hence their accuracy. And it's also regularly updated. We have moved from ERA to ERA 5 to ERA 5 analysis to ERA 5 land now. So just meaning how consistent and homogeneous the data sets are. I intended to make this an interactive presentation so I wanted to ask the people in the room, how many of you know Eswatini? But now that I'm doing it online, so I'll just tell you what Eswatini is. So previously known as Swaziland, it's a small country in the Southern African region, actually in the northeastern part of South Africa. So for those who have gone or visited South Africa, here you can see it as a small dot somewhere at the northeastern part of South Africa, and I'll give you a homework to now go check it, because yes. But the country has a predominant subtropical climate, and it has 5 major river basins that flows through and from Eswatini. The ones that flow through Eswatini are the Ngwavuma as well as the Mbuluzi. And those are the ones within, but the ones that flow through are the Pongola, Usutu, and Komati, as shown here. Well, the whole area has 122 individual sub-basins, and in South African terms, we somehow do not use the Strahler orders, but we use the orders in like primary catchment, secondary catchment, tertiary catchments, and quaternary catchments. And quaternary now are the last hydrological response units. From the 1960s, the Eswatini the monitoring systems has been on rapid decline, and currently there are only 72 stream flow stations, which are these green dots that you can see over here, and 51 rainfall and evapotranspiration recording stations. Then we classified the whole basin using different climatic land use, water use, and geomorphological characteristics, which helped us understand how RFI land performs under different hydrological conditions. And for the purpose of this presentation, I will just give the results of when we classified the Eswatini using the topographical characteristics, of which we came up with six classes: the escarpments, these blue parts, the flat high veld, the green ones, which are the upstream parts, and the low veld, the downstream, the middle veld, and the steep low veld, which form the middle part of the catchment, as well as the steep mountains, which are also part of the upstream. So we found that the variations in rainfall and evapotranspiration are largely as a reflection of the topography, where the mean annual rainfall varies from over 1,000 millimeters per annum in the escarpment areas and less than 600 millimeters in the low veld areas. A similar scenario is seen when we look at the mean annual evaporation that ranges between 1,200 mostly on the upstream and 2,200 on the downstream areas. Runoff is largely driven by a couple of factors, where in the western region these parts is driven by the steep slopes and intense rainfall events, while on the eastern lowlands, these parts, it's driven by mostly soil characteristics and vegetation cover. Now to my results. Through the first result is aridity index, where it's just the ratio of the mean annual precipitation over the mean annual evapotranspiration. And we did a correlation analysis. This is just a scatter plot showing how L5 land performed vis-a-vis the observed WR 2012, of which we saw that in as much as the correlation was okay, for example, when you look at the highs and the lows, they are falling almost at the same spectrum, but it didn't perform very well. And with the worst performance on this region, the steep low veld, and a better performance, but not a very good performance on the middle veld. When you look at the mean monthly runoff, we found there was a very good correlation of 0.86, which was very good. As you can see, the highs of 130 and almost the highs of 120 when it comes to both the L5 land and W2012 respectively. But when we created the scatter plots, we found that there was a very good correlation between the two data sets with, as you can see from the results here, with very good performance in the flat high veld and low performance in the steep mountains. For the 10th percentile, there was, which are like the high flows, it didn't perform well, as you can see from the results from the R square, but good performance was seen in the steep mountains, of course, because it's the high flows, and very poor performance recorded in the flat high veld. For the 50th percentile, the narrative became even worse, with better performance only seen in the steep low veld and worse performance seen in the middle veld. It got worse and worse and worse with as we were moving towards the 90th percentile, which are the low flows, with the steep low veld giving us a better performance, but very poor performance in the middle veld. When you look at the distribution of errors, it's quite evident that the mean monthly runoff had a wide spectrum of errors, but it was on the low side, with at most 30% of the results falling within the undesirable results. But you can see the opposite can't be said for Q90, where we find that almost all the results, almost 100% of the results had somewhat errors. So what we concluded is that there's a generally good agreement between the two data sets in terms of the mean monthly runoff, and L5 land performed better in relatively flat terrain, which are mostly categorized or characterized by croplands, shrublands, and grasslands, especially in Eswatini. But worst performance was in the steepy mountainous areas, which are characterized by forests. At first, we downloaded the monthly data, and we found that there was a lot of noise. The uncertainty ranges were very high, and that's why we opted for the daily. So we recommend that when you're using, if you can also use hourly, the better. So the finer the temporal resolution, the better. That's one of our recommendations. And in as much as it performed well, ERA5 Land also had its limitations, which could be attributed to the coarse resolutions and the uncertainties in the inherent reanalysis data. To conclude, we found that the hydrological process can inhibit considerable spatial variability, and the relatively coarse resolution of ERA5 Land may not fully capture localized responses and characteristics. And the table on the right shows how the ERA5 Land performed in different regions when we looked at the topography. But of course, if given another chance, if UNOSA gives us another chance to have another meeting, I will gladly present ERA5 Land performance on different vegetation cover, soil cover, as well as climate. So Nina, please, you can give us that honor again. So this is just an annex of how the Google Earth engine looked like when I was downloading the data, and I put all the 122 shapefiles into the engine. This is just one of them, and downloaded the data. I'm very sure some of you are very conversant with, as I saw from the previous presentations. Thank you so much, and yeah, let's connect. From my LinkedIn page is Harriet Okal, Twitter Harriet Okal, and you can find me at harriet@gmail.com or at my work email harriet.okal@acai.com. Thank you so much for the audience, and I welcome any questions at this point. Thank you.
So given that this is our last presentation, so we're going to open up the floor for anyone who has a question for Harriet or for any of the other presenters that we have had. So any questions? We have about 20 minutes, a little bit less than 20 minutes. So please, any questions for any of the presenters? You have some questions, Jim? Because I have a question for Nodira. Yeah. My question is, can you talk a little bit about the utility of your research for regulations and policies? Please, can you elaborate on that? Thank you.
Thank you for the question. As I mentioned in the presentation, the first goal of going into policy making is to firstly analyze how much of water do we have, so that we can further calculate how much is being lost, and the comparison, like projections, compared to the storage capacities and to the water that's being lost, so that we can put fair taxes and also regulate the issues with the end users. Thank you.
Has there been a specific case of any public policy being impacted by what you do?
As the project is very young, I think you are one of the people that are seeing it for the first time. We are negotiating it with different governmental organizations, and we've done a lot of work presenting the work. I'm not really sure about the policy part because I'm mostly into tech, but I know that some big changes are on the way.
Okay.
So yeah, we'll keep you updated.
Okay.
Thank you.
Great. Thank you. Jim, do you have any questions for any of the? Oh, is there? Do you have one? The microphone? You need the mic.
Good afternoon. Thank you, Harriet, for your presentation regarding the ERA5 land datasets. And like you mentioned, the performance of the datasets were better in the flatlands versus that for the mountain areas. And that I was wondering whether any bias corrections would help in improving the performance of them. And in terms of the steep areas, what was the difference? I mean, yes, you said it performs better than the steep areas performs worse than that of the plains. But what's the difference? Is it dramatic or is it acceptable limits? Yeah, thank you.
Harriet, are you still online to be able to
I
take?
am.
Did you hear that question?
I did.
Okay.
Thank you so much, Mandira. Very nice question. In terms of bias correction, we tried as much as we could to do bias correction, but at first we wanted to show how the raw data from Era 5 land works, and that is the results that I have shown. But of course, we are still doing some bias correction. And indeed, as you said, we found that the Era 5 land was performing better in flat terrains rather than in steep regions. And we found this also in different regions where we tested the Era 5 land. For example, in Zambezi, we also found that it performed better in flat terrain rather than in the steepy mountains, as well as the waterfall areas of the Zambezi, and also in Congo. And we also saw that in as much as it was not performing well, but the error margins were very high. So yes, it was a drastic change that we saw between the steep mountains and the low-lying areas. Thank you.
I'll maybe pose a question for discussion, and maybe this goes to all of the speakers, but anybody here, what do you see as the gaps in the technologies in delivering the space satellite information? What are the biggest challenges and gaps and the things that would improve our work the most? I don't know if there's any of the speakers that could respond to that, or anybody here. What are the most important needs and gaps that currently exist?
Thank you, Jim. In fact, I'm working in the same research field as you for the discharge estimation. From our application experience, we met that our end users thinks the result accuracy is very different with our scientists' view of this accuracy. Maybe we think 90% or 80% is good. But when we use this kind of data to their daily using monitor or assessment, they think this is not good because the result maybe we are very different with their field measured results. Then they will think, no, your result is not good. We can't use this. I think this is the gap. What we think from scientific view and end user views.
So are you saying that if you're 90% correct, but it still doesn't match their observation, that there's an unwillingness to use or trust the information?
We met this.
I agree. That's a very difficult thing. And it's also difficult from the scientific side. Sometimes I believe it's scientifically, we're not comfortable with 70 or 80% or an R of 0.5 or 0.6, even though it might be a good fit to us. We don't want people to use that information because we know there's limitations and errors that could be exposed. And so I think that is a really critical gap in terms of helping people understand, there are limitations and uncertainties with the science regardless. And I think we do have to be careful as scientists not to overstate our work, because we know that somebody's going to come along and show a different model, a different way of looking at it, could expose some errors. And so I think that problem of being able to communicate uncertainty and limitations is a really important part about using these kinds of technologies, whether it's in water resources or other space technologies, is being upfront. I like to use the example a lot of when I go to the doctor. I expect this is my health, it's sometimes in my life. And I think that doctor should be able to tell me exactly what's wrong with me and what the remedy is. And we kind of expect that, but the reality of it is we know they're experienced scientists making an informed guess at what's wrong with us. And I think that we also have to be able to communicate that in the technologies and the things that we use. We're experienced scientists using best technologies, but at the end of the day, there's uncertainty and limitations, and I think we have to be open and honest about communicating that. Other questions or responses towards gaps and needs in these technologies and how we apply them and use them?
Thanks. Well, from my perspective, it might be sad, but I think one of the biggest obstacles we often face in this kind of work, especially when it addresses hydrology and those kind of systems, is the lack of commitment of some of our governments, perhaps, when, I don't know, they may think that there's something we are not doing well, but they are losing somehow the perspective on what they should do. For example, in the case of my country, the number of hydrological stations has been reduced gradually from 70%, 50%, 40%. Because they think that was what they had to do according to the economic restrictions and economic issues that the country or the region has been faced. But by doing such kind of actions, they are affecting not only their actions, their past actions, but also affecting the future of the country and of the region. Well, I don't know if there's something we can do about the decisions at the political levels, but all it takes is to continue working to try to use as good as possible the technologies that we are trying to develop with the help of other governments, and just to continue working. I don't know if there's a solution on that.
Yeah, I think it's a good point. And I think Harriet's presentation kind of indicates this, and Mandira's comment about bias correction, because, here is good data, the ERA5 land data, but it has bias. And if we present that as, well, we have these technologies that provide the information, and we don't discuss the importance of having measured data that can help us understand the bias and improve the satellite information and global models, then we're going to be limited in their capability. We do need that, and it's very difficult to get governments to invest and maintain those kinds of stations, isn't it, Federico? I know Federico works in the WMO region here, and we works tirelessly to try to get that kind of information, to have those stations, to have it useful and corrected. It's not just because we have a station doesn't mean the data is going to be good, that it's verified. And so we as scientists, even using these space technologies, need to be able to continue to emphasize the importance of continuing to have ground-based monitoring so that we can validate and improve what we have. Other comments about that, experiences or other questions? Yes.
I think I'd like to add onto what you said about the difficulties of getting this in situ data. We work with very different in situ data, but in the end, some problems are shared. And one of my feelings is that sometimes getting the equipment at the start, it's easier than maintaining it in time. It's like getting the new equipment, you can get a grant or something to do that. It's sexier, so they will give you the money. Then 1 year down the line, 2 years down the line, when you say, oh, I have to recalibrate this, it's like, there is no money. And that's a problem because you're losing equipment that is very expensive, and after a few years, you can't use it anymore. And in some regions, at least for the kind of measures we make in South America, there is no capabilities to recalibrate equipment on spectrophotometry. So it's really difficult to continue to have data. Maybe your first year, it's good, and your second one is so-so, and it kind of lags. I don't know if that's a common problem, but I know that for us, it is. So just that sense.
My experience says that's a common problem. And I'm not sure what it is. Maybe the initial investment up front is much easier. Maybe we're not always as truthful about the full cost, right, of the measurements being in our desire to get the equipment in the first place, right? But we have to be honest, and we have to factor those things in.
Thank you. So I also want to think like community engagement is another factor. While most of the projects like have done really well in community engagement, but I think we still have a long way to engage our communities, especially to uptake what we're researching on, what we're working on, because at the end of the day, we're looking at what we're doing and how like whatever we're doing, sorry, goes back to the community, whether it's all about water resources, flooding, drought. So, and the aspect of biasness could be one issue why maybe communities don't want to take what we're developing to mitigate some of the problems they have. But I think we have a lot of work to work on community engagement and the end user. Yeah.
Maybe Nadira, could you respond to how you're engaging the community and how the information that you're developing? I know you said it's open and available. How are you getting that information out so that others can use it?
Actually, the project on the water is not quite open because of some strategical values on the water reservoirs, but the project that we developed on data sets, on tree monitoring, on land monitoring, mostly I think it has always been some kind of necessity for this, but people did not really know where to find this, and that's where we come in into the scenario and find those people who were in need of those. And we actually have a lot of contacts with them prior because their necessities is the first primary reason why we developed this. That's why engaging with community became quite easy.
Thank you. I think Tahendra online, I see your hand raised.
Yeah, actually, I have a question for everyone, and it's related to interbasin leakage. Interbasin leakage is a serious issue in the watersheds of the higher Himalayan regions and watersheds with highly undulating terrain. Is there any model that comprehensively includes the interbasin leakage, or additionally, is there any satellite product that can address this limitation? I'm just curious about this one.
You're speaking of interbasin transfer of water or just?
Yeah, interbasin transfer of the water, like as interbasin there is so like as there will be large, I presume that there will be large quantity of base flow that is leakage through intervention, like basin to basin. And then I don't think there is any comprehensive model that will encounter all the interbasin leakage.
Anybody had experience or could comment to that? Okay, Mandira.
Yes, thank you, Tejendra, for your question regarding the interbasin transfer. I think that is quite relevant, particularly in rivers that you mentioned, like for instance, in Nepal, we have the Melamchi River Basin where we are transferring a significant amount of water from the Melamchi River to the Kathmandu city for water supply. So for that, I would say, I mean, there is no, like, I think when Professor Nelson was presenting, no one particular model that is looking at, there's a suite of different models and a lot of different sensitivity analysis that can be run to analyze the interbasin transfer. So those are the scenarios that you can probably look into and then look at the interbasin transfer, because here you're looking at a certain volume of water that you are transferring for the particular river. And then for that, you also need to look at the ecohydrology of the river systems. So basically, that could be a number of different models that you could consider to look at what kind of sensitivity areas that you are looking at. So I think that would be my answer to you.
Tejendra, I could also point you to a group from Australia, CSIRO. They developed a model called Basin Futures that uses global data sets in order to develop scenarios for water development. And I know that they had options for interbasin transfers. And so I'm not quite sure the status. But I worked with them a couple of years ago, and so you might look at Basin Futures out of Australia.
Yeah, got it. Thank you so much, Nelson and Mandir ma'am.
Federico.
Thank you, Jim, and thank you for the reference. I'm Federico Gomez. I work for the WMO. WMO, this is the World Meteorological Organization, the regional office for North America, Central America, and the Caribbean. And I think that Jim just said two things that are very important and key to me. And I would like to reinforce those ideas. First, that hydrological observation is very expensive, somehow needs of commitment, or it's like a long-term commitment. There is a difference, and there is a number of reasons why this is so expensive. It is not the same that measuring other variables, let's say precipitation or temperature, and it's not the same measuring water levels than being able to estimate discharge, stream flow. So this is something that sometimes is not necessarily well understood. And there is a part of this that comes with a commitment. Sometimes it's, of course, the state, the government that makes that call and decides to really engage on that. But there should also be some alternative, innovative ways of doing this. But I'm talking about observation in the field. I mean, to go and get your feet wet and really look at the process, because no matter how advanced technology is, I think at least I haven't seen yet something that really can replace that. And that's what linked us to the reality, I guess, in hydrology at least. And the second idea is that along with these innovations and these discussions, is also all these very exciting. There is no doubt of that. And we expect to see these developing very quickly in the coming years. Again, we need to keep sending the message, in my opinion, from our perspective, our experience in Central America and the Caribbean, for instance, that we cannot faint on, keep pushing to convince governments, decision makers, potential investors on the importance of having these good quality observations in the rivers, and then to commit to keep this, because sometimes, as someone mentioned here, you get the money to start, and that's also very exciting. It's new, and you have some people trained, but then it won't last if you don't really understand how serious this commitment must be. So it was just to mention those aspects from our side. Yes, we do try to convince as much people as we can, the governments as well, in the importance of having good observing systems. And even though all these exciting technologies come up, and we will continue to see it to evolve, we won't, I think, faint on the purpose and the intention to increase and keep getting better and better observing hydrological systems in our regions. Thank you.
Thank you, Federico. I think that's an important thing that I also can't emphasize enough. In the GeoGlows that I presented, I kind of mentioned early on that it's almost like we have put a gauge in 7 million rivers and went back 80 years and kept the data. But the reality of it is, without 21,000 in situ stations, observations that we have integrated into it, it would not be useful. It would have it would show the kinds of bias and problems that Harriet mentioned in the lowlands, and there would be no way to improve that. And so even while I mentioned the improvement, like the example from Google Earth, in the quality, the resolution of the space observing systems, if we don't match it with the Earth observations, the in situ observations, that's where we can actually get the greatest improvement and over what the space technologies can provide. And so it really is important that we don't forget that really critical element of how we use space technologies. I think that, in Alexandre's example too, I think you mentioned you need the states, you need the local people who know where the rivers are, right? To be able to fully map and be able to take advantage of the DEM in order to get the information that you need. And without that level, there's a certain limitation that only the space technology can provide. And I will also kind of end with the example I mentioned with Malawi, which was highly successful in terms of its publicity because of how successful it was. But in terms of the community engagement, they already had their own observations, their own stations. They understood themselves what the importance of it was, so that when we were able to provide a longer term forecast, they knew exactly what to do with it, because they already had and were operating their own stations and their own, they had an understanding of what that technology could bring to them. And I think that's an important part of the capacity building and education, that we need to connect what we're doing to the ground, to the community, to the people who actually have problems that need to be solved, and connect what we're doing to their problems.